Okay, last time. So we had covered, let's see, we got as far as looking at the global L functions, but we were looking at local L functions individually. Did we define them?
I think you defined them and you said they're going to end up having a functional equation.
That's right. Right. So Tate's observation was that all this, when we do things globally, actually we can do things locally. And you could just piece together the L function just from the local data. So given a local character omega, so omega p, qp cross to c cross, although I'm going to start dropping the p's because once we're talking about local, it's just annoying to have them everywhere. I don't know, maybe I have to have them there. It's just annoying, but we'll deal with it. Given a local character and a Schwartz function, fp in Schwartz in qp, we have a local zeta function. I mean, most people would write zeta or z, the local zeta function. And it's subtly different from the local L function, but I'm going to abuse notation and I'm going to write the local L. I'm just going to write these things. But when you look in books and papers, you'll see Z for what I'm calling L. So what is it? It's just the local integral that we evaluated a bunch of these local integrals.
There's like some factor or something.
Yes, so often what people want to say the L function of the representation with no, the point is to get rid of any dependence on this arbitrary Schwartz function. So we're going to build up to the fact that this thing is independent of the Schwartz function. I mean, it's not independent as defined, but all of its key features are independent of the Schwartz function. Like as defined, here's the Schwartz function. You change the Schwartz function, you change the integral, you change the definition of this z. But all of its salient features, as far as the L function, the L theory is concerned, will be independent of F. If it's a good theory, it shouldn't depend on these arbitrary choices. Okay, so we have this character, we have this F, and then we have a complex number S, and we're going to take the p-adic norm of TP, raise it to the nth power, and integrate with respect to the multiplicative measure. Okay, these are exactly the kinds of integrals we were evaluating in special cases. So recall that if
data is packed into this character, right?
Yes, exactly. The character has all of the salient features.
Everything else is just kind of.
Well, the S is the complex variable, and the other things are fixed. It's the F that we don't have any control over. So we'll just make an arbitrary choice. But there are times when it's important to have flexibility in our choice of F. And actually, we'll see that now. That'll be good to make certain choices of F to be able to evaluate things. So recall that if this this omega p is unramified and fp, I'm going to start dropping p's. You'll forgive me. Is the indicator function of zp, is the p-adic Gaussian, then this zeta integral. So now you'll see what I mean about this zeta integral is the local integral is the local L factor. In other words, 1 over 1 minus chi of p over p to the s. So that's the subtle distinction between, there's no F here. Well, we made a choice here. But I claim that the salient features of these zeta functions are independent of F. Here we did make a choice, and by themselves, you can't treat these things as objects by themselves, but you can treat them as objects in terms of functional equation and analytic continuation. So, okay, so the first thing we have to do, so this was a computation that we carried out. The first thing we have to do in order to make this computation legitimate is to see where this converges absolutely. So lemma, this z. Okay, so I guess I will use z. I'm so used to it. I tried to call it an L function, but no. Okay, fine. We'll reserve L for this guy. So this integral, as defined, converges absolutely in the range, and let's figure out what that range is. It had better converge somewhere. So what's the range of absolute convergence? So let's prove it, and then we'll figure out what it is that we're proving.
Thus, homomorphism.
And thus has holomorphicity. Yes, exactly. And thus is a holomorphic function in S and that. Okay. So so what do we know about absolute value of ZP? So we'll use the triangle inequality, bring it inside. Now the F function, this test function, is Schwartz, locally constant, compactly supported. Compactly supported means there's some compact set, some set of the form p to the minus capital N times ZP that contains the support of F. And it's supported on a compact set, so it's just bounded. So the value of F, so I'll write absolute value of F here, but I'm going to replace this by a constant. What else do we have? We have absolute value of W, omega, that's 1. And then I have TP is a complex, well, TP is a real number. I'm raising it to the power S. So that's TP, the pth root to the real part of S power, and then D star P. So this is just triangle inequality together with compactness and the size of the character. Does that make sense? We've done integrals like these before. Yes, we've evaluated these integrals, but I don't think I remember convincing you that this local integral converges.
Yeah.
But it's very simple. So I'm just bringing the absolute value inside the integral sum.
Oh, that's triangle.
Yeah, I'm adding a bunch of things. This is adding it and then taking the absolute value. This is taking the absolute value inside and then adding them all. And the only observation is that I don't actually integrate over all QP cross. I only integrate over some piece. There's a finite amount of negative powers of P that it can occur because of the compact supportive F. Okay. And so, well, this is very simple. Let's break this into a sum over what the actual value here is. So this is a sum over little n going from minus n up to infinity, and then an integral over TP in p to the little n ZP cross. In other words, just tell me what the actual absolute value of TP is, and that absolute value is p to the minus n to the real times real part of S, D star P, D star TP. Right.
C.
Yeah, with the constant C out front. Thank you. Let me yeah, okay, fine. Good. So this is an integral over a multiplicative integral over a translate. I mean, it's the multiplicative Haar measure, multiplicative translate of ZP cross. This has total integral. One. And so all we're doing, so that has integral 1. Here's a constant. All we're doing is summing a geometric series. Okay, there's some positive, there's some negative values of n which turn into positive powers of P, but only finitely many of those. And then we have lots of negative powers of P. So we have a geometric series. This is some finite sum. This is a geometric series in P to the minus real part of S to the nth power, summed as n goes from 0 to infinity, plus a finite number of terms, plus finite terms. Okay, so what do we need for this geometric series to converge? We need the thing that we're taking powers of to be less than 1. So if that thing is less than 1, that means that the exponent of P is in fact negative. So the real part of S had better be positive. That's it. Real part of S is positive. So the local zeta integrals actually converge all the way down to real part of S bigger than 0. When you multiply them all together, of course, now they only converge when the real part of S is bigger than 1. But okay, so we were perfectly fine in making these kinds of evaluations. Which part? Oh, the fact that what did I say? Of course, dude.
When you multiply them all together, then you lose like a strip of convergence.
Yes, you lose a strip of convergence because if they're all of the form 1 minus 1 over p to the s, each of these evaluations that we did here, they are make sense, they are valid as long as the real part of s is positive.
Oh, yeah.
But when you multiply all these together, now you need more convergence
Right.
to make sense of that product.
Instead of like from 0 to 1, they could be big numbers. Right?
Well,
You
we just don't
multiply
have-
them together and like.
Multiplying this out is the same as summing chi of n over n to the s. And the harmonic series diverges, but any power greater than that. Okay, so putting them together is just asking for a lot more information.
Right.
Okay. So fine. So these things do make sense. So my next claim is that they have a functional equation. So lemma. There exists a meromorphic function, meromorphic gamma, depending only on omega, such that the z function of f has a functional equation with omega going to omega bar, f going to the p-adic Fourier transform, and s going to 1 minus s. And notice that this is independent. The key is that notice is independent of f. This is independent of f.
So then you can do the quotients thing that you talked about. Right?
Exactly. Okay, so this is the next thing we want to know. The proof of this is very simple. What we can do is, what does this really mean? So where do both of these things make sense? Remember, this converges if the real part of s is bigger than 0. This converges if the real part of s is exactly. So in the real part of s between 0 and 1, both of these things make sense, and we can look at the quotient. What we want is that the quotient zp omega fps over zp omega bar
It's nice.
fp hat 1 minus s is independent of f. In other words, it's the same if I replace f by some other function g. So is this the same thing? Is this the same thing as if I take the zp but now with a g, and same with a g hat for g for another Schwartz function gp? How can you prove that this is the same? Well, let's cross multiply and see what we get. We'll get a double integral. Yeah, so let's look at zp omega p fp s times, if I cross multiply, I want to look at the product of that with zp wp bar gp hat 1 minus s. Okay, let's look at the product of those two things. Again, we're in the region of absolute convergence for both of these integrals to make sense.
It suffices to look at one of them, right? The other one.
Yeah, so the point is this product will be independent. And that'll tell us that when we replace f by g, we'll have exactly the same integral. And so this quotient will be a holomorphic function, which we will define to be this gamma. It's a little yes. Yeah, this Tate made all these lovely observations in his thesis. Okay, so what's the definition again? We're integrating over QP cross omega p TP f p TP. The p, you see how annoying it is to put the p's everywhere, but I don't have a better idea at the moment. I guess I could just stop writing p's everywhere. Hopefully we'll know that these are the local. Yeah. Yeah. All right. Let's keep it as is. Times the same integral, QP cross, omega p bar of some other variable, let's say UP. Now, that's the same thing as putting the 1 over, all right, let me just put the bar, but this is the same thing as 1 over UP, right? UP is invertible. Omega is a character, so it's the same thing as 1 over UP. GP, okay, I do want more space. Yeah, I want more space. Yes. Although here, if I could see past the Zoom thing, I could copy and paste the thing. Anyway, so again, WP UP bar, G hat, and then TP, not T, but U to the power 1 minus S, D star U. And what is G hat? It's the integral over QP, not QP cross, of GP, I need a new variable, V. You remember our character, our p-adic character, e to the 2 pi I, VP, what's the variable? UP. Additive character, D, VP. Let me give you a minute to write all that down. Okay, all we're doing is writing out the definition of ZP, writing out the definition of the other ZP, and writing out the definition of G hat. Okay. Now, the point 0 has measure 0 in this integral. This is the additive par measure. It gives size p to the minus n to p to the n ZP. The intersection of all those p to the n ZPs is 0. And so I can remove the point 0 without affecting the integral, which is QP cross. That's right. But I don't want to write QP cross yet. Once I've removed the point 0, v equals 0, I can make a change of variables. In fact, that's independent of that. I can make a change of variables replacing UP by UP times TP. Okay, so for fixed TP, let's move this all the way here so that the integral, this big integral, is inside there. So a fixed value of TP, I can make a change of variables. UP goes to UP times TP.
This is, but you're doing change of variables.
In U. So I'm going to, this is hard measure, so that's not going to change anything here. Let me not do it all at once. Let me keep track of what I'm doing. So WP of TP, FP of TP, TP to the S, you'll see in a second. So then I have an integral in QP cross. Now I'm changing UP to UP times TP. So I have a W bar of UP and a W bar of TP. Then I have the G integral. So this is an integral also over. Now I will write QP cross. GP of VP, e to the 2 pi I, VP, UP has been replaced by UP times TP. Then there's a DVP, which is just hanging out. So DVP, so far so good. Then I have a UP, so the 1 minus S, and U became replaced by U times T. So now I have a T, P to the 1 minus S, D star U, and D star T. Okay, hopefully we followed all of that.
So you did this change of variables and what did it affect exactly?
Well, at the moment, all we did is we used it to kill off the WP of TP here and here.
But using the character.
You're using that it's a character, but it's absolute value as well. Okay. The other thing, yes. Yes, the other thing, am I missing anything? There's one thing that I wanted to come out. All right, let's take this TP to the S and TP to the minus S and rub that out. Also, here we have a TP to the 1 and D cross TP. Remember what the par measure is. It's some constant. In fact, that constant is P times P minus 1 times TP.
So that just like died out.
So those two are canceled. Okay, so we have additive Haar measure in TP, additive Haar measure in VP, a constant. So let's write this again. So I have a triple integral in QP crosses. I have an FP of TP and a GP of VP and E to the 2 pi I VP UP TP. So what do I have so far? This, and this. There's this U. There's a UP to the 1 minus S. Nothing I can do about that. There's this constant P over P minus 1. I've got that. Got that. I just need the character UP omega P of UP bar. And that's everybody. And now comes D cross UP, DVP, DTP. And this is symmetric in F and G. It's symmetric if I replace F by G. It makes no change in the integral. The T and V variables are completely symmetric. Okay, so this is symmetric. That's exactly what we wanted to know. So this product is independent on replacing F by G and conversely. Show the whole thing again?
Yeah.
So all it is taking these three integrals. The three integrals are the two integrals defining ZP and the one integral defining G, making one little change of variables. Everything falls away. And all that's left is a triple integral with F at TP, G at VP, e to the 2 pi I, VP, TP, UP, and then everything else is just U's. And then we have a DTP, DVP. It's completely symmetric in F and G.
You just get rid of the hat and on the G and then.
Yeah, we just wrote out what G hat was.
I know it's surprisingly more powerful, changing, combining integrals and changing of variables internally.
Yeah.
It's symmetric, so low.
So what? So the quotient. So if we take so now we know that this thing is the same when I replace F by G.
Okay.
So I take quotients this way and that way, and I find that ZP omega P FPS divided by ZP omega bar P F hat P 1 minus S is the same with FP replaced by GP for any other GP.
I mean, or I guess you could just say the other cross multiplication would be literally the same.
Right. So if I define,
But you plus that. Oh,
we proved a global functional equation, actually.
we put the range is not different than that.
We did last time. Maybe I stated it.
You stated.
I stated it.
Yes, okay.
And here's the proof of what I promised.
Okay.
Okay, so the point is this ratio does not depend on F. Because you replace F by G, you get the same thing. So that means I just take any F and I take this quotient, and that's this. I claim that there exists this meromorphic function. What is it? Choose any F, take the quotient, it'll be independent of the choice of F. That's my gamma. Okay, so let's evaluate it, right? So what is it? It's nice to have an existence formula, but it's much nicer in some sense, in some cases. In this case, we can actually write down what these things are.
I have a question.
Yes, please.
When you take that quotient, do you lose any analytic information? Like, are those functions ever zero? Do you ever have like a divide by zero at some values of s kind of problem?
Yep.
Okay.
I know nothing about the where those zeros might be. It's meromorphic. Yep. At the moment, I don't know anything about its potential poles. And in fact, it will have poles because if you, so recall what this thing is in this case. In this case, I mean, you can make, just solve this thing is equal to, just solve this denominator is equal to 0. Right? S is going to be some complex number. Like log, whatever. It's a elementary algebra. So at those values of S and their shifts by 2 pi I, this thing is going to have problems. If it is to be analytically continued. So by the way, now we have an analytic continuation. Well, we have to like, let's work this out in one case, in one easy case, and then we'll have analytic continuation. Okay. Or at least meromorphic continuation. So let's exhibit, let's find these guys. Let's compute these things. Okay, so case 1, p equals infinity. By the way, I keep writing qp cross, but this we also have local integrals at infinity. So let's see what's happening at infinity. What is this z infinity, omega infinity, f infinity? Which f shall I choose?
Right. So what happens is multiplication of infinity?
Everything is exactly the same. The only difference is instead of f being, well, it's not exactly the same. It's not exactly the same. It's, well, if you think of q infinity as r, then almost all of this goes through. So certainly this computation, we never used anything. Okay, there's a constant that isn't there for the real place. It's just TP over absolute value. I mean T infinity over absolute value. The question about, I guess I didn't prove here, I didn't prove that this thing converges if f is Schwartz in the real sense.
If you're Schwartz.
But if you're Schwartz, then actually it converges even better. There's no power that gives you problems here. Okay, so again, this is an integral over r cross. This thing will be omega infinity. So what is omega infinity? You remember that this is either 1 if chi of -1 is 1, or it's the sign if it's -1. Okay, so this is either 1 or the sign. Okay, so let's say, by the way, I don't know if I can't remember if I use this language. This is called unramified at infinity, and this is called ramified. So if the infinite place is unramified, let's work on that case, unramified, then I choose unramified. If unramified, I choose fp to be the Gaussian, e to the minus pi. Don't make me write x infinity, x squared. Okay, then I'm integrating over r hat, e to the minus pi x squared. Omega is 1, and then I get x to the power s dx over x.
It's ramified on x.
Exactly. Yep. Okay, this integral is twice the integral from 0 to infinity. The integral from 0 to infinity we worked out already. It's like pi to the minus s over 2 gamma of s over 2. And so if that's the case, and of course f infinity hat is f infinity itself, the Gaussian is its own Fourier transform. So if that's the case, then the local factor at infinity, the unramified local factor at infinity, is just the quotient pi to the minus s over 2 gamma of s over 2 divided by, so that's the value on this side. On the other side, I have a w bar, which is the same as w, f hat, which is the same as f, 1 minus s. So everything's the same except I'm replacing S by 1 minus S. Okay, and this evidently is meromorphic everywhere. So this is meromorphic in C, in all of C, with some poles of the gamma in the bottom giving me zeros and some poles of the gamma on top and so on. So it really is, it's not just holomorphic, it's meromorphic. Okay. What if it is ramified? So what if we're at the infinite place but ramified? If ramified, then I choose, in other words, chi is odd. I have -1 is -1. I choose f infinity of x to be x times e to the minus pi x squared. Anybody know what f hat is? If you stick, I did tell you last time. Yeah. Right. Is it I or minus I? I think it's I. I think it's I. Either I. Yeah, that's right. Okay, in which case, and what does the integral come out to? So then Zp is again integral over r cross. I have the character, which is sine of x. I have the test vector x e to the minus pi x squared. Now x times sine of x is the definition of absolute value of x. And then I have absolute value of x to the s dx over absolute value of x. So this is literally the same thing as before, except with s replaced by s plus 1. So this is twice pi to the minus s plus 1 over 2, gamma s plus 1 over 2. That's z. That's z. When I replace f by f hat, I get just a constant factor I out. So gamma omega infinity s in the ramified setting is the quotient pi to the minus s plus 1 over 2 gamma of s plus 1 over 2 divided by I times the same thing with s replaced by 1 minus s. I times pi to the minus 2 minus s, I guess. Let me just write 1 minus s plus 1. Let's not do arithmetic. Unnecessary arithmetic. Okay, again, the point is this is also meromorphic. Also meromorphic.
Gamma's gonna have poles and those.
Yep. And 1 over gamma is going to have zeros and no poles.
Kind of crazy that you can multiply all these things together and then you don't get like a zero limit or anything like that. Or breaking everything.
If you did, you would, if you had a zero limit point, then the whole function would be 0.
Right.
And we can evidently choose values of f where it's not identically 0, which means you can't have a sequence of limit points of poles or zeros. Yeah. Okay, so that was the p equals infinity case. Either ramified or unramified, we can work out exactly what the gamma factor quote. Can you see why it's called little gamma? It's just a ratio of gamma factors. What's the p-adic analog of that? So case 2, p unramified. Okay, what will I choose for my FP? The Gaussian, the indicator function of ZP. We already did this integral, as we said. ZP is 1 over 1 minus chi of p over p to the s. So gamma p, gamma omega p, if omega is unramified, is the quotient, this thing on top, and switching to 1 minus s and chi goes to chi bar on bottom, except with the surplus. Okay, nothing to do there. We can work out explicitly what gamma is, even if we're ramified. P is ramified.
We did some stuff with ramified before, right?
Yes. Yeah. But the point is we can actually evaluate these things explicitly. So if P is ramified, let's work out what the ZP is. So ramified, remember what that means. Omega P, the kernel of omega p contains 1 plus p to some power, k, l, what do we use? E, L, p to the LZP with L minimal. With L minimal. Well, that's just the definition of conductor,
Right.
is the smallest
And
L.
we actually needed this.
We actually need this. That's right. That's right. Then recall, if P is ramified, then the kernel is this, and omega P of some power of P times a number M in Z mod P to the L Z cross plus P to the L times anybody in ZP is what? So this is, it's chi. It's chi of M. Chi of M, and in fact with a bar.
Right. So you ignore the power.
You ignore the power, you ignore anything after the Lth place, and only this matters, and it takes the value of this term. Okay. So we can work out what Z. So now let's work out what ZP. We need a choice of F. So ZP, omega P, FP, S. What should we choose for F? We'll choose FP to be this indicator function. The indicator function of 1 plus P to the L ZP. Instead of the indicator function of ZP itself.
Almost be able to using X.
That's right.
The X case.
That's right. If it's ramified, you have to adjust your choice a little bit. Okay. Do we remember what F hat is? What's that?
At least the boarding function. Like. There's something.
Oh, it's a boring function. You'll see. It's actually quite an well. FP itself, maybe I agree, is a little bit boring, but FP hat will give us some fireworks. So what is it? Do you remember? If you translate what happens in the Fourier space, rotate e to the 2 pi I c times a in this case is 1. You get a negative power of p, and then the indicator function of p to the minus LZP. Okay, so let's just recall that is a calculation that we have done previously for this choice of F. Okay, so what is this? It's an integral over QP cross omega P TP FP of TP TP P through P norm to the S D star TP. That's just the definition. FP is the indicator function of 1 plus P to the L ZP.
That's what the support is.
That's the not just the support, but the definition. So 0, 1. It's exactly the indicator function of this set. So we're only integrating over this set. What value does omega take on this set? It's the kernel. So it takes the value 1. So this takes the value 1. This we've replaced by the indicator function. And what about TP? What's the absolute value? What's the pth absolute value on this set? It's 1. It's a unit. It's 1. Okay. Let's remember what TP cross is. TP cross is TP dTP divided by the absolute value of TP times this factor P over P minus 1. And TP is, again, just 1. The P absolute value of TP is 1. We got rid of almost everything. There's this factor of P over P minus 1. And then what is the additive Haar measure of this set? It's a set where the only freedom is in the last, well, in the last infinitely many places, but the places after P to the L. P to the minus L. Okay, that was pretty easy. all we have to do is work out ZP of omega bar F hat at 1 minus S and take the quotient.
Like a constant of S.
This is a constant in S. This is a constant in S, yes. So again, it's not the ZPs, it's the quotients of the ZPs that will give us,
So you get the hat base and you get.
well, let's see. Let's see. So ZP of omega bar FP hat at 1 minus S. Okay, integral over TP cross omega P bar of TP. F hat, should I put in what F hat is already? Let's put in what F hat is. F hat is e to the 2 pi I TP, P to the minus L, and then the indicator function of P to the minus L ZP of TP, of whether TP is in this set. Okay, that's F hat. And then we have absolute value of TP to the 1 minus S. And then D star TP. Let me write out D star TP as, well, yeah, let me, here, let's leave it as D star TP for a second. So far, so good. Okay, this indicator function of TP, yes. I want to break this. So let's look at this. Let's look at this. TP is in P to the minus L ZP. Okay, so it looks like, well, potentially some P to the minus L, but it could be some smaller. So let's write TP as P to the minus N, where N is the power in front of. So N is at most L times a number that's in ZP cross. But I want to decompose that number in ZP cross as the first bunch of terms plus P to the L times the rest of the terms. Okay, so M is in the finite set Z mod P to the LZ cross, and U is in ZP. Does that make sense? Any element in P to the minus LZP, what does this mean? It means, you know, this is something like A minus L P to the minus L plus A minus 1 P to the minus 1 plus A0 and so on. Okay, but I don't know that A minus L is non-zero. So where's the first non-zero term? So I have to, so P to the minus N somewhere, could be over here, wherever the first non-zero term is. Then what is the first L, what are the first L coefficients of that? And then the rest. Okay. So effectively, we're making a change of variables. And this is why I do indeed want to change this to the additive. So let me replace this by dTP over absolute value of TP times P over P minus 1. Yeah, there's almost no difference. Okay, so there's one more thing, which is the term Z. Oh, the 0 is not in there anyway. Good, 0 is not in there anyway. Okay, so 0 is not there because we're summing over. There is no value of N for which the term 0 would be there. So it's this thing intersect QP cross, which means this thing take away 0. Good. Does that make sense? Yeah. Okay. So this integral is a sum as N goes from L down to negative infinity, but I'm going to break that into N goes from L down to 1 plus a sum as N goes from 0 down to negative infinity. Okay. So N is, oh, the TP decomposition?
Oh, yeah, it's like M plus EL.
So what I'm saying is, where is the first non-zero digit? The first non-zero digit has to be at least, at most, to the right of P to the minus L. So n is at most L.
Point that out gives you a unit.
Gives me a unit. I want to take the first L digits of that unit. That's an element of Z mod P to the L Z cross, because the first digit's not zero.
Make it positive power of that.
And then I take P to the L, and then anything of the later coefficients. Okay, so I'll sum over n, and I'll sum over the finite set m mod P to the L, but only the ones co-prime to P to the L. That's exactly what this sum is. And then I have a change of variables, U replacing TP, UP, I don't know. We have enough P's floating. Right? So now we have just a change of variables, which is an additive shift that dTP is invariant under, and a multiplicative shift, which we're not invariant under. So let's record dTP is equal to, what is this? P to the L minus N, P to the L minus N du. When we make this change of variables. So we're breaking into a finite, well, here a finite sum, there an infinite sum, a finite sum on M, and then the integral on T is replaced by an integral on U.
Still don't see it.
Well, I haven't done anything yet.
Oh.
I haven't written anything yet. So I'm just saying I'm making a change of variables, replacing U, replacing T with U.
Oh, I guess like I don't see why you have to different.
So this is the additive harm measure. The difference between T and U for fixed M and fixed N, this is just a constant.
Oh, we would change the variables with respect to you.
Yes, I'm saying U is my new variable, my new
Oh,
variable
right.
of integration.
Either minus that.
Yeah, for fixed N and fixed M. So there's an M sum here as well. M mod P to the L prime. And now I have to integrate over U. U in ZP. Integral over U in ZP. Okay. So far, so good. I have a WP bar of TP. What happens to WP bar of TP? TP is this. W on something of this form, W on something of this form is just chi bar of M. So the shifts in P don't make any difference. The U doesn't make any difference. It's just chi bar of M bar. So I just get chi of M. Okay, that's this term. Then, oh, there's this constant P to the minus L. Fine, let's keep track of that. P to the minus L. Here and here. P to the minus L. We've got that. The indicator function we've got already. E to the 2 pi I TP.
Why do you do something?
Well, I just broke the case N, the integral into whether TP is in ZP or not. So if this N is 0 or lower, then this thing is actually in ZP itself. If it's in ZP itself, then e to the 2 pi I TP is just 1. So that's taking care of the character on this side. On this side, well, it's e to the 2 pi I TP, but actually N and the P to the L, it has nothing to do with U. It's just e to the, I don't have room to put it somewhere, so I'll put it here, but it's not a function of U. It's e to the 2 pi I M over P to the N. I'll write it like that. The U part just dies off. Okay, so now I've taken care of the character. Then I need this T to the S. Okay, so T, absolute value of T to the S is absolute value of T. If I've written T as a unit times P to the minus N, the absolute value of T yeah, T is P to the minus N, so its absolute value is P to the N. P to the N. There's a TP to the 1 and a divided by 1. So actually this divided by 1 and that 1 cancel. Oh, there's another constant P over P minus 1. Let's just get rid of those. P over P minus 1. That N is not intertwined with Okay. So I've taken care of that constant. I've taken care of that constant. I've taken care of the character. I've taken care of 1. So this has absolute value p to the n. So this is going to be p to the n to the minus s. So that's p to the minus ns. P to the minus ns. And then dtp. dtp is p to the L minus n du. P to the L minus n. P to the L minus n du. Yeah. Hopefully you can still make out what's here. It's really not that bad. In fact, let's make an immediate observation here. Where's the m dependence? The only m dependence, because the character is always 1, the m dependence here is just in the character, and we're summing over all the values. That gives me 0. This whole thing is gone. 0. The chi.
That's why you broke it. Right?
That's why I broke it. Okay. Let's look at this. What is my u dependence here? There's no u except for this integral. That integral is 1. Okay. So let's write things nice and good. P over p minus 1 is a constant. P to the minus L is a constant. I have a finite sum, n going from 1 to L. I have a finite sum over m mod p to the L, chi of m, only those m's that are coprime to p. And then an e to the 2 pi I m over p to the n, and then a bunch of constants, p to the L minus n, p to the minus ns. Okay, so all I did is I rewrote what we had up there, getting rid of the integral, which is fine.
What is the original integral?
We are trying to evaluate zp, so we can divide this by that. Okay. We have, so these things actually come not all the way out, but they come here.
It is a finite sum at this point.
It's a finite sum, but I'd like to evaluate that finite sum. What do I have here? M ranges mod p to the L. I have a character, primitive character mod p to the L. It's almost a Gauss sum, except it's e to the 2 pi m over p to the n, not over p to the L. Bless you. What happens to those? If I sum m mod p to the L,
And it is smaller than
right, n ranges from 1 to L.
so then.
Yes. Yes. If n is strictly less than L, what do I get?
We do this computation.
We did a version of this computation. I think we actually did. I think we did this computation. Yeah.
But when they're equal, right, and that's just.
Yes, when n is equal to L, this is literally the Gauss sum, tau of chi. It's like, if they're not equal, it's like having a p to some power over p to the L. So it's the Fourier transform at a value that's not coprime to m, to p. It's 0. It's 0 because this you can decompose into the p to the n sum on the inside, and then inside of that, a sum over the other digits, and the sum over the other digits of chi is going to be equally spaced around the origin. So this is 0. So the only term that contributes is n is equal to L. The only term that it contributes is n is equal to L, in which case I get p over p minus 1. This p to the minus L, let's get rid of. I have a p to the minus n to the 1 plus s, I guess. P to the minus n to the 1 plus s, but the only value of n that contributes is when n is equal to L. So now I've taken care of that. This thing is the Gauss sum, and that's it. This thing is the Gauss sum. You can evaluate all of these things with choices, with special choices of test functions. So Kirill, do you still think this one's boring?
Yes.
But its Fourier transform is fun.
I get to see more. Maybe.
We'll have to do more things there, certainly. Yes. We won't be able to just evaluate it. We want to have nice formulas like, oh, it's just the character on some simple set. Yeah, so what can we conclude? What we can conclude is if P is ramified, with conductor P to the L, conductor P to the L, then this gamma omega P of S is, let's see, it's the original value, this Z thing, which is this, P over P minus 1. What was it? P to the L? P to the minus L? I've forgotten already. P to the minus L. That's divided by the value of this integral, which is what we just computed.
It's great that you know that Gauss sum is not zero. You proved it earlier. Otherwise,
Yes.
you'd be in trouble.
That's right. That's exactly
That's
right.
the absolute value for the conductor, square root of the conductor.
Square root of conductor. Yeah. Yeah. And we'll see that'll come up in just a second, actually. Okay. Well, we can simplify these things, but it doesn't matter. The point is this quotient is seeing the Gauss sum, which plays a crucial. Okay, so let us indeed simplify. These things get simplified. There's a P to the minus L on top and on bottom. And I get a P to the L S divided by tau of pi.
It's like, and L just came from the choice of the plus function.
Well, L was the conductor. L is the
Right.
conductor of P.
In the case of that omega.
Yeah.
Whatever it is, it's L.
So again, this is meromorphic. Okay, so once we have meromorphic, once we've worked out all of these gammas, we have their meromorphic continuation, which means we can get meromorphic continuation from this formula, wherever it is, here. This thing makes sense now for real part of S less than 1. They agree when real part of S is also greater than 0, but now we have analytic continuation of this everywhere.
Multiply them all together.
That's the next step. That's the next step. Okay, is to take these things and put them together. Before we do that, let me note that the gammas themselves have a functional equivalent. So lemma. The gammas themselves, gamma omega of S times gamma omega bar at 1 minus S is something. Let's work out what that something is.
Why are we doing this?
Well, there's more. So the gamma itself has its own functional equation. I just want to make that observation.
Right, needs to.
Yes, I mean, it will.
Think
So-
that the other, the thing it's multiplying has one, right? So
That's right. That's right. And in fact, that's the proof. So this gamma. So what is this gamma? Or let's look at it this way. If I take this ZP omega FP, I make any choice. This is regardless of whether P is ramified or not, I make any choice of FP. That proof was independent of ramification. This thing is equal to this gamma omega P of S ZP of omega P bar FP hat 1 minus S. But this thing also has a functional equation, ZP of omega p bar, FP hat, 1 minus S. If I replace, so this is going to be a gamma bar at 1 minus S times ZP. Now I'm going to replace omega bar by omega bar bar, which is back to omega. I'm going to place FP hat by FP hat hat.
You normalize it so that that would be.
No,
Something.
no, I did not. I normalized FP hat to only have e to the 2 plus 2 pi I. To invert the FP itself is the negative of that. So FP hat hat, FP hat hat of X is actually F of negative X. But in this integral, I can make a change of variables. X goes to negative X. So this is just an aside.
You added it 4 times. Then you would have-
That's right. But I don't want 4 products of these things. So this is ZP of omega P of negative whatever FPS. And omega is a character. So omega P of -1 comes out. Chi of -1 comes out. Chi of -1 comes out, and I get it omega P bar 1 minus S times CP of W F S. Okay, so but this thing is equal to this thing. So I get that chi of -1 times omega P bar 1 minus S times omega P WP at S times the same function, ZP W bar F hat 1 minus S. So this thing had better be 1. And that gives me the functional equation that this thing is not 1, but chi of -1.
So that's why you multiply them together.
Right. Okay, does that make sense? In fact, let's test that here. This was true whether there was ramification or not. Okay, let's test that. Test when P is ramified.
This is the one you just find.
Yes, but math won't be broken. We'll actually be able to learn something. So that's this gamma omega P of S, which we computed a minute ago. It was P to the L S over tau chi, P to the L S over tau chi. And so if I take this thing, if I take this gamma omega P and multiply it by gamma omega bar at 1 minus S, what do I actually get? So I put in the value of this, P to the L tau of chi, and I put in the value of this. So that's P to the L 1 minus S. Instead of tau of chi, I have tau of chi bar. P to the L and P to the minus L minus S cancel. Now, do you know what tau of chi is? Did we talk about this? So there's it turns out, so this is a fact, I'm not going to take the time to prove it, but if chi of -1 is 1, then this is just P to the L over 2. And if chi of -1 is -1, then this is I times P to the L over 2. Tau, yes, I'm sorry. Tau is the Fourier transform at 1, or unnormalized Fourier transform at 1. It's the sum over M mod P to the L, chi M e to the 2 pi I M over P to the L.
How difficult is the value of this?
Gauss spent quite a lot of time. Gauss was very proud of observing what the sign is. The fact that the absolute value is L over 2 is easy. What the sign is not that easy.
This is one of his published results. Really
Yes, he did publish this. So check out what we get. We get a p to the L on top, and on bottom, well, we get a p to the L over 2 twice. So we get a p to the L, and then we get either a 1 if chi of -1 is 1, or you get an I squared, which is -1 if chi of -1 is -1. Also known as chi of -1. The top and bottom cancel, and I get chi of -1. So this, all I wanted to point out is that this functional equation, let me wait for you to finish writing. This functional equation we said was going to come out to chi of -1. We shouldn't be surprised by that it comes out to chi of -1.
Actually, this is the
But it's hiding this Gauss evaluation of the Gauss. Okay, anyway.
We use
Good.
it as a proof of that Gauss evaluation.
Well, yeah, almost, yeah. Yeah, you could turn it the other way around. That's
this is like a weak version of Gauss.
yeah,
Something. So,
okay. Good.
multiplier together.
What else can I do in the last 10 minutes? Yeah, let's finish our crash course with the Rankin-Selberg method. Okay, so let's talk about Rankin-Selberg L functions. So okay, you put these. I'm trying to think of what I can do to really close everything up. We've thought about the local theory. There's a slightly more. I need to go into a little bit more depth to get the epsilon factors all together and multiply them all together and go just from the local theory to the global theory without. We already did the global theory from Poisson summation, but actually you can go back and forth, and that's really useful when we go to GL2 and even higher.
It'll give you some information.
Exactly. Here everything's so simple, we can do all the integrals, and so we don't see the difference between what integrals are difficult and what integrals are easy. Let me do one thing that I think I can do in 8 minutes, which is the Rankin-Selberg convolution.
At some point you will show us, the product of all these, the bridge, the local.
Yes. But right now, let's do a global Rankin-Selberg integral. Okay, so what's the Rankin? This is called the Rankin-Selberg convolution. It's a process that takes. It's sort of the first hint of what Langlands discovered. It's a process that takes L functions and makes new L functions out of them, at least conjecturally new L functions. So there's a sort of. Should I give you the general case? Yeah, let me tell you what it is in general. So if you have an L function, if I have an L series, L of S, well, I'm going to do it just purely abstractly. An L function abstractly is a finite product, a product of, well, let's say n going from 1 to, let's say it's a degree D L function. And then a product over primes of 1 minus some numbers, alpha sub n of P over P to the S inverse. So let's call this L alpha. I'm calling that a degree D L function. The L functions that we've seen so far are degree 1 L functions, GL1. Okay, product over all primes, and we saw characters here. But in fact, yeah, this is really starting to give away some of what the Langlands philosophy is as games on the Langlands-Satake parameters. So these are sometimes, we call them Dirichlet characters, but let me give you a fancy name for the same thing, so these are Langlands-Satake parameters. Langlands-Satake parameters. And if we have another L function, L beta S, which is degree E is not a bad letter to use for degree, is it? Let me make it E. Actually, my L's and E's are pretty similar. So you can take that to be an L if you prefer. beta, let's call this M ranging from 1 to E, just so that beta M of P over P to the S inverse. Okay, then the Rankin-Selberg L function, L A cross B of S, is a product over N from 1 to B, a product over M from 1 to E, and then a product over primes, and then the product of the parameters, alpha N of P, beta M of P over P to the S inverse.
Interesting.
This just,
Starts with this other stuff, it sort of starts with the sum side, and then when it
That's right.
eventually gets to this.
that's right, but that's really what Langland's discovered, is that the sum side is the wrong way to do it. The sum side is a mirage. It works for Rankin-Selberg, at least on GL2. It works whether you look at the sum side or the Euler product side, and it was first discovered on the sum side. But to understand how this principle works in general, you really want to go to the product. Yes.
It's like a lot of work, you know, you have.
Yeah, yeah.
Fundamental domains and the unfolding.
So I'm hoping we'll get to the adelic version of that.
Really.
But right now, let's just do the GL1 version of what a Rankin-Selberg convolution is for GL1. Okay, so for GL1, which is all we've built up so far, GL1 adels, let's say we have two automorphic representations, phi1, phi2, are automorphic representations, irreducible.
Oh.
Yeah, they come with characters. So this is induced. Phi1 is corresponds to Dirichlet character chi1. Phi2 corresponds to Dirichlet character chi2.
Right. We're in GL.
So the L function of phi1, the global L function now, we're back to this is a product over primes, 1 minus chi1 of P over P to the S inverse. And the same thing holds for I equals 2. And so here D and E are both 1. In the case that D and E are both 1, we want to make an Euler product, which is just the product of the Dirichlet characters. This is saying something actually trivial. The product of Dirichlet characters is a Dirichlet character. Okay, so the L function of the Rankin-Selberg product, will be 1 times 1. It'll be degree D times E, but 1 times 1 is still 1, of 1 minus chi1 of P times chi2 of P over P to the S inverse chi1, chi2. I'm putting P's where they don't belong. Okay, and how can we, so this is what this L function is. Can we find this L function by some kind of global integral? So recall, so for F, a adelic Schwartz function, we have our theta function of F, which is a sum over Q in Q cross F of QT. And what I want to do is look at the following integral, the integral over the E dels modulo the rationals, which is where the theta function is defined. It's also where phi1 is defined. It's also where phi2 is defined. I take these things, I multiply them by the adelic norm of T to the S and adelic harm measure. And I look at that integral. Okay. In 2 minutes, what can I say? Well, let me just say, same calculation as always. In other words, you unfold this to an integral just over the E dels themselves of F of T, P1 of T, P2 of T, T to the S, D star of T, and then just make the observation that the phis are really Hecke characters, that the automorphic representations are Hecke characters, products of Hecke characters are Hecke characters, corresponding to the Dirichlet characters, the product of Dirichlet characters. Same calculation as always leads to that L function. So there's really nothing, there's nothing all that interesting that needs to be done in order to get the product of Dirichlet characters. But I want to think about what happens. By the way, why is it called a convolution? Well, maybe some stupid people gave it a bad name. That's always a possibility. But these are actually some very smart people. What is it? Oh, why it's called a convolution? Oh, I like the name. Uh-huh. I'm happy to argue with Henrik. I often do. Especially about things as silly as names. Leads to, let's just finish the statement, leads to the product, the Rankin product L function, just because it's all GL1, it's all abelian characters, product characters. The character, you just pretend that this thing was itself a single character who's corresponding to the product of the Dirichlet character. Everything else is going to come through. Why convolution? Since I'm out of time, let me say why is it a convolution? Well, when you take the product of two things, if I take f times g and I take its Fourier transform, that's the Fourier transform of the products. No, it's not. It's the convolution of the Fourier transform. Okay, so here I'm taking the product and I'm taking a kind of transform of that product. What I get on the other side, we should call a convolution of the L function. And in fact, well, there's a way to make this precise on the level of Dirichlet series. So if I have a Dirichlet series an over n to the s, and I have another, so this is LAS, and I have another series LBS, which is a sum of bn over n to the s. Then it turns out that the Rankin series, Rankin-Selberg convolution of these will be an times bn over n to the s.
Right.
And this is so if you think of these as the Fourier coefficients, it's like taking the Fourier transform to go from the L function to the A's, and same thing from the L function to the B's. Then you take their product and you take the inverse transform to get back to the L function. So it is indeed the same shape as a standard convolution. All right. I think that's all I'm going to say. There is more to say, but I encourage you to read, Bump chapter 3.1 or Goldfeld chapter 2 or whatever it is. I'm going to add some more homework. And we'll go back to classical. We'll start talking about the classical GL2 theory on Friday. And try to move into the, after spring break, move into the adelic GL2 theory.